In the last part of this lecture, I want to derive a formula for the entropy change of an ideal gas. And this formula will be valid in any process. It doesn't have to be isothermal, isobaric, isochoric. Any process, the formula that we get will be true for an ideal gas. So before I get started with the ideal gas for the entropy, I want to give you an example of something which isn't a state variable. So the special thing about entropy is that it's a state variable. So I'm going to show you the difference between when you're working with a state variable and when you're not working with a state variable. So let's go back to the first law of thermodynamics. du is equal to dq minus dw. And q and w are not state variables, which is why we put the little notch on the d like that. So maybe let me write this as dq is equal to du plus dw. And then du, you remember for an ideal gas, is nm cmv dt plus dw. So here I specified to an ideal gas. Now, this is generally true for an ideal gas. Now let's suppose we specify to a reversible process. The first term is unaffected because it's only deals with state variables anyway. And then the work done in a reversible process is PdV. That's the process, the formula we've been using the whole time. And now maybe I want to get, for example, I want to try to get an expression for the heat added in some process starting from some initial point to some final point. So what you might try to do is say, let me start and try to figure out what is Q going from initial point to final point. Well, that would just be the integral dq, like that, right? Starting at some initial point, ending at some final point. And then since dq is up there, so this is a reversible, heat added in a reversible process. So I would have here nm cmv dt plus integral p dv. I to f, I to f. Okay. The first term I can do, so nm cmv, and then here I would have tf minus ti. That's fine. But this second term, I can't do this integral, because in order to do this integral, I need to know p as a function of v in order to do it, right? If p is constant, I could pull it out, but if p is not constant, I can't. And so I need to know the path. To do this integral. I need to know the equation which describes this curve in order to do that integral. And that's as far as I can go. So what it shows you is that Q, I to F, in a reversible process, depends on the path. If you give me a path going from I to F, I can put it in here, do the integral, and get the value for Q. But I can't do it in general. This is as far as I can go. That's because Q is not a state variable. Okay, so that's just an illustration of how it works, how far you can go if you don't have a state variable. And now let's do it again, but let's do it for entropy and see how it works. Okay, so I'm just going to start exactly the same way as the previous slide. So I started with the first law of thermodynamics. I plugged in the fact that U only depends on the temperature for an ideal gas. So, and that's all I've done so far. Now again, this relationship here is totally general, but now let's specify to a reversible process. And then I can put in here PdV, because that's the work done in a reversible process is P times dV. Now you might get worried. You might think what I'm doing here is not totally general, that I'm only doing something for reversible processes, and we'll show that in fact this will be more general. And then what I'm after is S, right? So I need to use here ds is dq, the heat added in a reversible process, divided by T. So I better divide both sides by T. So I'll have dq ReV over T is equal to Nm CmV dt divided by T plus P over T dV. Okay. The left-hand side is ds. Okay. Now suppose I want delta S, I want the change in S, which I would get by integrating ds. So that means I should integrate both of these terms. dt over T from some initial temperature to some final temperature plus P over T dV. This is as far as we got before when we were doing heat, but this is looks better. The first integral I can do no problem. The second one, you say, this looks just as bad as before because I need to know P as a function of V. However, I know that by the ideal gas law, P over T is Nm R over V. So this is ideal gas law. So then I got the following, Nm CmV. I can pull out those, integrating from Ti to Tf, dt over T, plus integral. The integration variable here is V, so I better put limits that make sense with V, Vi to Vf. And then P over T is NMR over V times dV. And notice what happened to that second integral. Now, this is a constant which I can pull outside, and then I've got dV over V, which I know how to integrate. And in the first integral, I've got dt over T, which I know how to integrate. So notice, I don't need to know anything about the path to do these integrals. I don't need to know the path to calculate delta S. And that should not come as a surprise because S is a state variable and it doesn't depend on how I get from one place to the other. It's path independent. Okay, so now all we have to do is just do the integrals and then we'll have our formula. So just carrying over the formula from the previous slide, I have two integrals and they're both natural logs. Very simple to do. So Nm CmV, this is the natural log of T, evaluated at Ti, Tf, and then I have the Nm and the R come outside, and I have here the natural log of V evaluated at Vi and Vf. And hopefully natural log of Tf minus natural log of Ti is the natural log of Tf over Ti. So using the rules for logs. So hopefully that doesn't come as a surprise. And then I can simplify my formula for delta S for the gas. For ideal gas, it's equal to Nm, and I can pull that out because there's an Nm in both terms here. And then I've got CmV natural log Tf over Ti plus R natural log Vf over Vi. So here is a formula which is quite important. And the amazing thing about the formula, if you go back and look at the derivation, is that we started by playing a trick and it said, let's specify to a reversible process. But the formula that you get at the end depends only on state variables. There's no information in here about reversibility or reversible processes or how I get from one place to the other. All it depends on is the initial point and the final point and constants. So this, therefore, is valid for any ideal gas process. It doesn't have to be reversible. It could be reversible or irreversible. So if you're ever trying to calculate the entropy change of an ideal gas, you should go to this formula because this one is true for an ideal gas. A common mistake that students make is sometimes they use this for liquids or solids. And a dead giveaway that you can't use that for liquids or solids is the presence of R. R is called the universal gas constant. So if any formula has R in it, universal gas constant, it's only valid for a gas, not for a liquid or a solid. The other thing that sometimes confuses people is delta S. Remember, S is specific entropy, so that's delta, the capital S, divided by the number of moles. So if you want the specific entropy, which is entropy per mole, you would just divide by this Nm there. So it's the same formula without the Nm if you want the specific entropy. If you want, you should go back to the previous lecture where I talked about free expansion of an ideal gas or isothermal expansion, and you could use this formula in both of those cases and you would get the right answer. So this formula is very, very powerful for calculating entropy change of an ideal gas.